UC Davis Graduate School of Business. As some of you might know, UC Davis has a business program right here in San Ramon. So we connected, iValley connected with the UC Davis office, and we talked to Amy, who's here as well, and talked about collaboration and all. And UC Davis does a lot of good work, obviously a lot in ag tech and things. But Professor Naik has done a lot of work around big data, especially in marketing. And I think he has a wonderful presentation. And please welcome Professor Naik.
She blinded me with science.
Well, thank you everybody for attending my session. My name is Prasad. I do marketing research, primarily focused in marketing dynamics and dimension reduction. Marketing dynamics is about how your current action will affect future outcomes. And dimension reduction is about how many variables can be reduced to a few factors so that we can meaningfully understand what is going on in big data. Today's talk, I'm going to talk about the second part of my research, which is about dimension reduction. You guys must have heard this 3 V's, and then there are many other V's that got added into the soup, value, veracity. But to get the point, I want to just emphasize the classical 3 V's, where volume is about the storage. So over the last 20 years, computational power has increased so much, and the storage cost has gone down exponentially, that we just have a large data. And by data, we typically meant 20 years ago, a little table of numbers, some rows and some columns. And that table could become larger and larger. So you could have Excel, and Excel cannot open it. So we have SAS and various things, but they were all numbers. And so that was the issue of volume. But then soon we realized that more than 90% of human information is not numbers, it's words. So we talk, we say something, we mean something, there's emotions, and all those words eventually went into text mining. So last 10, 15 years, there's a lot of research on text mining, and that added up the variety. And then, of course, in the last 10 years, we have other forms of data. It could be images, it could be videos, it could be many other formats, and that's the variety part of the 3 V's. And velocity refers to how quickly it updates. Okay, so whatever data set you may have, previously we would say, well, this is an annual budgeting cycle, and so we would get the numbers in September, figure it out what to do in October, in November we make our plans, and then for 1 year we just implement that. And then annual become quarterly, quarterly became monthly, monthly became weekly, and now you got clickstream data, and it could be even nanoseconds. Okay? So it is continuous stream of data, and that's the velocity. But the consequence of all the 3 V's and other V's that I didn't speak of is that we got big data. So the size is big, the variety of formats is big, and they get updated very rapidly. So the data matrix that we are now looking at used to start with small n and p, where n is the number of rows. So usually they are the observations. And p is the columns, and those are your variables. And that used to be a table in a textbook, and then it became an Excel file. And then it became larger because the computational cost went down. And then, of course, we got all kinds of formats and started updating rapidly. And we not only have a lot of rows or the samples or observations, but we also have many variables. And so the size of variables have now exceeded the number of observations you could have. And so now the question is, what does big data really mean? If you ask that question, most people will give you a different definition as to what they mean by big data. I'm going to confuse you even more by giving my definition of big data. And so most definition of big data is size related. So how many terabytes of data you have. Big data doesn't have to be size because the size itself is changing. So once you get more energy, more computational power, more powerful computers, what was big then is small now. And so the definition of big data in the abstract has to be big independent of constraints, at least thought constraints, of energy or computational power. And so in the standard theory, when we think about big data, we allow the sample size to grow, and the sample size can go to infinity. So your observed sample may be 100, 1,000, whatever the number. But the theory on which statistics is based allows the sample size to increase to infinity. But the number of variables are kept fixed. So there may be 100 variables, 10 variables, 5 variables, whatever they are, but they are fixed. And because P is fixed, the number of variables, and the sample size increases, the ratio of number of variables to sample size goes to 0. And so all classical statistics has this property that the number of variables remain constant, sample size increases, and the data, that the ratio converges to 0. And so you get a matrix, which is a tall matrix, many rows and fixed number of columns. And that's called P less than N. So you have fewer variables and much larger sample size. Even with very large data, if P is fixed, the classic statistics works. But suppose number of variables itself starts increasing. So every time you have variables, let's say 20% more than the sample size. So if you're 100 sample size, you get 120 variables. If you're 200, you get 240 variables. If you're 1,000, then it's 1,200. So the ratio P by N does not go to 0. Okay, so you allow sample size to increase, and we say, well, let variables also increase, and let P also go to infinity. Let's not keep it fixed. And let it increase at a faster rate than the sample size. And then P by N remains big. It's a constant. It doesn't go to 0. No matter how much P you observe and how many N you observe, the ratio P by N remains a constant rather than 0, which is what happens in the small data. And so that is the main distinction in the abstract, in mathematics, as to what it means by big data. And this definition or understanding of big data is free of energy constraints, meaning it doesn't matter what computation you are doing, it doesn't matter which computer you are using or what electricity you have. So long as P is larger than N, that is a big data. And N can be very small. N can be 20 observations, and P can be 25. Your classical statistics like a regression would not work. And you still need, even for a small data, but P larger than N, you would need some new results. So that's what we mean by big data. So in standard small data world, we will have large N, but P is smaller than N. In the big data world, in modern statistics, the 21st century statistics, the data matrix is also the P exceeds the number of sample size. And we want to now try to do some estimation and inference in a context such as this. So we got big data, lots of big data around us. But if you ask a question, where are the insights? And normally there are very little insights. So insights doesn't pop up from the big data. And part of the reason is that the insights have to be extracted from the big data. And to extract that insights, so the insights do not reside in the data. Insight resides into your mind, which leads to a model, which you estimate, and then discover that insight. And so that process has to come from you, that what is the model that I'm going to use to learn from the data? And if your P is larger than N, then there are two challenges that impede the discovery of those insights. So when N is large, but P is small, but N really large, like 10 million observations, it's a non-trivial problem even to compute, to store, to retrieve the data set, compute the average, which is a simple formula. Add up all the numbers, divide by N. I give you 10 numbers, you can do it back of the envelope. I give you 100,000 numbers, now you really need a computer. And if I give you a million or more, then you really need a big computer which can actually read it correctly, and hopefully the program is right so that it computes the right number, because there's no other way for you to go and verify by adding it separately. And so you get computational challenges of storage, retrieval, and computing. If one computer is not enough, can we have multiple computers which will do it in parallel and then combine the results? Can we do it in real time? And all those, or do we do it in batch or multiple batches fast enough so that it is as if it is real time? And all those are computational issues. If P is less than N, the classic statistics needs no modification. But if P becomes N, even if N is very small, you won't be able to use classical statistics. And so there are oblong data or long data for which we face statistical challenge. So there's computational challenge, and then there's statistical challenge. And statistical challenge is that if P is larger than N, then standard techniques won't work. So you've got 10 observations and 12 variables. You cannot invert a matrix. You cannot do regression. You cannot do any analysis by the standard techniques that you learned in school or college. So linear regression is a classic workhorse. Logistic regression is a workhorse to classify. Principal components is a way to combine variables. Factor analysis. These are standard methods. And all of these methods, in one fell swoop, do not work. And that is not about large N or large P. It is about P greater than N. And so we have this problem as to what do we do to circumvent this problem. About 20 years ago, a professor in Stanford, Tipshirani, he came up with a classic idea. He said, I can add something called sparsity constraint and then do the same methods again. And so this concept of sparsity paves the way to analyze any big data, and P can be larger than N. And it generalizes all of the statistics to a big data analytics. It's called Sparse Analytics. And everything works. The name changes a bit. It's called lasso regression rather than regression, sparse logistic regression, sparse PCA. And so that idea of sparsity. So let me explain what does sparsity buy you. So there are books that are out there that will tell you that you can incorporate sparsity, and there are many ways to do it. And I'm not going to get into the technical details. But if any of you are analytically minded and understand to read the Greek I put up here, like James would, you would easily realize what is it that it is saying, that instead of doing the classical problem, I'm going to add some additional constraint which will allow some variables to go to 0. I can add another kind of a constraint called elastic net. And then there are many, many ways by which you can add those constraints. And those constraints largely are called sparsity constraints. So I want to give you an intuition as to what does sparsity buy you. Sparsity says that if you have, let's say, hundreds of variables, you got the big data, but you don't want to really know all the variables that could affect an outcome. What you really want is an insight that of those 100, which few, maybe 4, 5, 7, 10, are really the ones which do affect the outcome. Okay, so the data set allows you a possibility of saying if all possible variables did exist with you, which are the few nuggets that I can collect. And so those nuggets is what you are after. You're not after the big data. But if you have the big data, the computational and statistical challenge impedes you from getting to that discovery. And to get past that hill, you need this bridge. And that bridge is the sparsity. And it allows you to shrink many irrelevant variables to 0 and only include relevant variables. So it's a technique by which you can exclude irrelevant variables and include only the relevant ones. And they could be few, 3, 4, 5, 6. And that's what you need for decision making. You want to focus on what really matters and exclude a million things that do not matter. And the big data, we don't get insights in the classical way, precisely because now we've got a million variables and we don't know which one matters. And so in gene array and biological sciences, there's a very popular technique. The human genome could have 100,000 genes. But you really need to know those 2 or 3 pairs that can affect cancer, or 2 or 3 pairs that can affect Alzheimer's. And so you can do gene therapy if you can isolate those few genes which really cause certain ailment. And so that's the technique which is generally used in those fields. It can be used even in business, and I'm going to give you 2 case examples as to how I have used it in my research. So one is the Super Bowl ad, which you guys watch all the time. I'm going to tell you something about that. And another one is about videos. So in the Super Bowl ad, it is about text. So we do text mining and then say, well, we got so many variables, and what really matters. In the second example, we have videos of CEOs and entrepreneurs who make a 1 minute long pitch, and we want to see what actions of their speaking, the non-verbal part, affects the outcome, in this case, the charisma of the speaker. All right, so here is the simple observation example from my marketing paper, which is under review, so I can't really tell you a whole lot, but I can tell you the gist of it. So you want to figure out, of those 50, 60 ads which were telecast on Super Bowl, which of them were liked by the customers, and then what factors actually drive them. And so one of them is the budget. So did you spend a lot of money? Was it shown 10 times or 3 times or once? Did you do it last year? Did you always do it? Was there a teaser campaign before that? So all matters of money. And so that is one factor. It could be the characteristics of the ad. So was there a dog in it? Was it humor in it? Was there a person in it or something like that? So those are the features of the ad itself. And that leads to certain factors, like was it informational? Oops. Hello? So was it informational? Was it transforms you, meaning you feel warm and fuzzy and you really like it and emotionally connect to the brand? Or is it motivational, which inspires you to go act and buy or do something or write something on Facebook? So those are all characteristics of the ad, which the makers of the ad does it, so ad agency and the company. Then there are factors about consumers. So consumers, when they see this, they go and write something on the Facebook. And we take all the comments of all the 60 ads in 2015 Super Bowl. And we also replicate that on 2016 Super Bowl. And then we factor analyze. So there are hundreds of words, hundreds of thousands of words, which leads to just few factors, whether they were thinking in a certain fashion, was there a positive sentiment towards the ad, was there an engagement with the ad, and all those are factors related to consumers. And then, of course, the ad and the consumer both are embedded in a context of the Super Bowl. And there's a game going on. And the game could interrupt, and therefore you may not actually like it. And so the quality of the game is a context. So the context could be the score of the game, the difference in the closeness of the scores between the teams, which makes it how exciting the game is relative to the ads. And it could be the serial position. So was the ad the first ad in that pod? Or was it the last ad in the pod? Or was it in the middle? And so the serial position in which the ad appeared, that can affect the liking, regardless of the budget and the consumers. And so there were 3 broad factors, one of the makers of the ad, one the users of the ad, or consumers of the ad, and the third is the context within this creators and consumers unfold. And so we run some factor analysis and then find out which of these things really matter. And it turns out that 60% is really consumer sentiment. About 20% is creators and 20% is the context. Going in, we thought that it is really the game status matters a lot. People kept telling us that, oh, if the game is exciting, then ad is an interruption. People will not like it. Or if the game is boring, then ad itself is why people watch Super Bowl. And so we had this hypothesis. Turns out, no such thing. The game context, the actual status, has very little percentage, 0.1% of 20%. So it's like 0.2% impact on how much you like an ad or not. And so that's kind of insights you could get by taking a large data set. So there are many, many variables here which loads onto each one of them. And so, classical word is called deep learning. So you have a factor, the factor itself loads on another factor, which loads again on another factor. So this is one layer of factor, oops. And that loads on another layer of factors, which eventually loads on the object of interest. Standard regression and factor analysis cannot do this, and we use some technique called sparse factor analysis, and we developed ourselves, and we analyze this data. There's another case example I will give you, which is about the video. So we took 22 sales pitches. So this is in Europe, a doctoral dissertation a student of mine is doing in University of Vienna. And real salespeople and sales meaning CEOs and founders, and they would make a 1-minute pitch, sort of a VC presentation about their venture. And we videotaped their actions, so all the gestures. And we wanted to figure out that does the way you speak and the gestures you use, so your hands are balanced, your feet are balanced, whether you're walking or having a cyclic motion, whether you're scratching your head, all that technically can affect your charisma. And so we asked people to go and rate the charisma of the speaker based on that video. And now we want to see what actions or gestures. So we do gesture mining, which is a new thing. So no words yet. We are focusing on nonverbal communication. And there are hundreds of variables. Your left hand can be up and it's not symmetric. Both hands can be going up and that's symmetric. Both hands can be tight and you are nervous. And all those factors could then affect your charisma. And here we have hundreds of variables, but only a small sample of 22 sales pitches. Classic regression would not work because you got 22 observations, 100 variables, and I say, well, which one of these 100 really matter? And the answer is, well, very few. But the question is, which few? And that's what we are trying to analyze, and then see that, what should be the right combination of gestures you should have so as to have the maximum charisma. So that's the dissertation about, but that's one technique where big data with sparse analytics can lead to insights, which big data alone cannot get you. All right, so that's my general pitch, that you will have the big data, but you will also need the tools of sparsity. And that techniques have been researched in statistics and machine learning and operations research and many other fields, including marketing science. And 20 years of research is ongoing. And so it predates Google and Netscape and internet. The paper where it started is by Tip Shirani, is in 1994. And so there's 20 years of research since then on how to optimally find the right sparsity constraints to get you the insights. There's a lot of new techniques have come up in the last 20 years. And that has led to a lot of new curriculum. And now that has led to a need for people actually being familiar with this new curriculum. And so UC Davis has started a program called Master of Science in Business Analytics. But before going to that, I want to just close this talk very briefly, that big data needs sparse analytics to be able to generate or extract insights. Okay, so if your goal is to learn something useful from the big data, then you need the bridge of sparse analytics. Data alone is not going to speak. Data is mum. It is a method that allows you to extract the insight. If your P is less than N, no matter what size, your standard classic statistics will work. If P is greater than N, no matter what size, your standard statistics won't work, and this new statistics that I'm referring to will allow you to cross that bridge. There are many ways to do sparsity, and it all depends on the goals of the project. And of course, we therefore need to understand how to match sparsity with the client needs on what is it that goal needs to be achieved. And of course, I gave you examples in marketing, but it applies, as I said, in gene therapy, and I hope it applies even in finance. So I'm no expert in finance per se, but I'm sure the technology of sparse analytics will apply to any field. This new curriculum, as a result, allowed us to launch a new program. It's called Master of Science in Business Analytics. You guys know this concept of data science, but data science is still very technical. At the end of the day, you still need managers, and so we want to apply data science to the domain of business. And so we started this program. It's called MSBA. It's a 10-month-long program. It starts next year. So we got final approval from the president of the University of California, and we are ready to launch. We will launch it, the class begins in fall 2017. There are two types. There's a 10-month program, and then there is a 19-month program. So if you have a job and you're working and you want to finish it, then you can do a 19-month program. It's a flexible track. Or it can be a fast track that you do 10 months, start to finish. You start this fall, and in summer you're done. And so that's a fast track. So there's a fast and flexi track. the key ingredient that differentiates us from all other programs, which will deliver this curriculum of sparse analytics, machine learning, Hadoop, R, all of that stuff, is that one component is the hard thing, which is the data and the analytics. So you just have to know all that. So somebody has to teach you, and you got to learn it. But then there is another important aspect, which is normally ignored in most curriculum, and that is a soft aspect. And that is the business aspect, which is the domain knowledge, and then the collaboration, the way you pitch it, the practicum on how to apply, get the buy-in from the client, give the solution, listening, oral presentation, written presentation. And so there are many soft skills that you need. And that balance is we have 50-50. And so we are going to have a program where we will not just claim that it is important to know the soft skills. We are going to actually inculcate in our curriculum the soft skills. There's a website, I don't know whether you can note this down, but if you type MSBA or whatever UC Davis, it will pop up. And of course, you guys can help us. So we really need everybody's help, yours most importantly. The first thing is that we haven't started enrollment, and so we need people to come and learn. We are looking at a very small size of 40 people, so it's not a very difficult thing to accommodate. But we want 40 good people. It's not just we want 40 people. And so, of course, we need your help in encouraging some of your employees to apply to this program. The second thing, the second thing you can help, The second thing you can help is that you can contribute a real data, live data in your company, and we will have 4-member student team, which will analyze and tackle that problem over a 10-month-long period. So it's not like a 3-month internship at the end. And so we will have a real program where from the fall itself, they will start with problem formulation with you to understand what the problem is, collect the data, see what your goals are, what needs to be done, what additional data we need, how to do this analysis, and then in the final quarter actually present you the insights. And so it's going to be a whole long engagement with the client and the student team, and of course supervised by the faculty. And there are many IP-related issues that needs to be worked out, and confidentiality of the data and all that. But that's a dialogue that we would need. If you guys are interested, definitely get in touch with me. I'm going to give you my email address at the end. And of course, you can be guest speaker, you can be an adjunct professor, you can be donor. I don't need to tell you that, but of course, you are free to do that. Not just for this program, but we already have an existing MBA program. And my colleague, Amy Russell, who is here, you can meet her. We have a standard MBA program where you get to think strategically. This is more about thinking analytically. And so that's a differentiated program. And if you are really interested in that, there are a few seats left in Bishop Ranch, 15, which is just a mile away from this place. And so if you're interested, meet her. She would tell you what next steps needs to be done to start in fall 2016. Of course, you can start any other time in the future. But if you are in a hurry, then she's right here. All right, so that brings me to the end. We got about 3-4 minutes.
Questions for Professor Naik?
So any questions if you have, feel free to ask. Looks like no questions.
Okay.
All right, thank you.
Thank you.